Hi, in this video we are going to calculate the Fourier transform of the rectangular pulse, but we are going to choose a special form of the rectangular pulse signal, which is known as the rect function in the literature. Let x of t be the rectangular pulse signal rect of t defined as, now x of t equal to rect t is equal to 1 for t between minus 1 over 2 and 1 over 2 and 0 elsewhere. Okay, so if we plot x of t, it is the rectangular pulse. So this is x of t, which is equal to rect t. It is equal to 1 for t between minus 1/2 and 1/2 and 0 elsewhere. Okay, so what is the Fourier transform of x of t? So we denote Fourier transform by capital X letter. X evaluated at omega is equal to from minus infinity to plus infinity x of t e to minus j omega t integrated with respect to t. Remember how we interpret the Fourier transform. The Fourier transform is just a measure of how much e to j omega t is contained in x of t by means of the analogy with the inner product. So this expression can be visualized as the inner product of x of t and e to j omega t, that minus sign coming from complex conjugation operation. Okay, so this is equal to, now x of t is only non-zero from minus 1 over 2 to 1 over 2. So we will have from minus 1 over 2 to 1 over 2. X of t is equal to 1. And we have e to minus j omega t integrated with respect to t. So x of omega is the integral of e to minus j omega t. So the integral is e to minus j omega t divided by minus j omega evaluated at these integration limits. So we have e to j omega over 2 minus e to minus j omega over 2 divided by j omega. Okay. So now we recognize the numerator as 2j sine omega over 2. divided by j omega. So the terms j will cancel out, and we can move this constant 2 to the denominator as follows. We have sine omega over 2 divided by omega over 2. Okay, so this is the Fourier transform of the signal known as the rect signal, the rectangular pulse, which is equal to 1 for t between -1/2 and 1/2 and 0 otherwise. So we have x of omega given by this expression. Now it is clear that when omega is equal to 0, this is equal to 1. And then when omega is equal to integer multiples of 2 pi, the numerator becomes 0. So we have 0 crossings when we plot x of omega. So now, if you wish, first let us look at what happens at omega equal to 0. Okay, let us express sine omega over 2 in terms of its Taylor series expansion. So sine omega over 2 can be expressed in terms of the Taylor series omega over 2 minus 1 over 3 factorial omega over 2 raised to the power 3, etc. We have the higher order terms. So sine omega over 2 divided by omega over 2, when omega is evaluated at 0, is equal to 1, because, as you see, when we divide the Taylor series expansion by omega over 2, this term will cancel out and it will become 1, and we will have powers of omega. So when positive powers of omega, when omega is equal to 0, those will be equal to 0. They will reduce to 0, and we will end up with 1. And the zeros of sine omega over 2 are located at omega equal to 2 pi k, k plus minus 1 plus minus 2. So we have these integer multiples of 2 pi, both for positive integers or negative integers, 1, 2, etc. So we have the 0 crossings. So if we plot the Fourier transform with respect to omega, we are going to end up with an expression which is in fact just the sinc function. Okay, but how can we convert this result to the sinc function, and how do we plot the Fourier transform? So let us now look at this problem. Okay, so let us remember how we define the sinc function. Sinc of, let us choose the argument as u. Sinc of u is equal to sine pi u divided by pi u. So this is the definition of the sinc function. Now, our Fourier transform, x of omega is equal to sine omega over 2 divided by omega over 2. So in order to convert x of omega to the sinc function, we multiply the terms omega over 2 both in the numerator and the denominator by pi over pi. That means we multiply and divide by pi. So with this operation, we have sine pi omega over 2 pi divided by pi omega over 2 pi. So x of omega is sinc omega over 2 pi. Okay, so our Fourier transform of the rectangular pulse signal, rect t, is sinc omega divided by sinc of omega divided by 2 pi. Now, if we plot x of omega as a function of omega, okay, we have the so-called main lobe of the sinc function. Then we have the side lobes, etc. We have such a graph. So the zero crossings are at if you look at the expression, when omega is equal to 2 pi, omega over 2 becomes pi. So sine pi is equal to 0. So this first zero crossing is 2 pi. Then we have 4 pi. And this one is 6 pi, etc. So on the negative axis, we have minus 2 pi, minus 4 pi, etc. So these are the zero crossings of the sinc function. Okay, now we have interpreted the Fourier transform as a measure of how much e to j omega t is contained in x of t for a particular omega. So you see from this graph that for certain frequencies, the frequency content is positive, and for certain frequency intervals, we have a negative value for the Fourier transform. So you can have a feeling of this behavior of the Fourier transform as follows. Remember that x of t is, in fact, we are trying to find the frequency content of x of t, and we express x of t in terms of the frequency components. This positive and negative weights obtained in the Fourier transform, I call it a weight because it is in fact a measure of the frequency content in x of t. So those positive and negative variations are essential in the representation of x of t, because remember, for most of the time axis, x of t is equal to 0. So in order to achieve this behavior, and we have a sudden jump at -1/2 to 1, and then again it drops to 0 at 1/2. So x of t can be synthesized in terms of the superposition of frequency components with positive weights and negative weights. Okay, now there is also an important detail related to this example. In the literature, sometimes the Fourier transform is expressed in terms of the frequency measured in hertz, f, instead of omega, which is the angular frequency. So we remember that omega is equal to 2 pi f. So if the Fourier transform x of omega, let us write down the expression once more, x of t e to minus j omega t integrated with respect to t. So instead of omega, we can substitute in this expression omega equal to 2 pi f, and we obtain the Fourier transform expressed as a function of f rather than omega. So it is from minus infinity to plus infinity, x of t e to minus j 2 pi f t integrated with respect to t. So if we go back to our sinc function, or rather, if we go back to sinc omega over 2 pi and substitute omega equal to 2 pi f, we have x of f given as sinc of f. So this is a result which is very easy to keep in mind. So the Fourier transform of rect of t, which is the rectangular pulse, which is non-zero between -1/2 and 1/2, is equal to sinc of f. Okay, so this is also a point we have to note, because the Fourier transform given as a function of f is also common in the literature. Okay, thanks for watching.